Hey everyone, this is Mr. Beckstrom, and today we're going to take a look at finding the complex zeros of a polynomial function. And we're going to write f in factored form. Okay, so the first thing that I want to do is I want to see how many solutions I should have. Now remember, complex means both real and imaginary solutions, and we just learned the fundamental theorem of algebra, which states that for a polynomial of degree n, and this one's a degree 4 because it's the highest power, we should always have four um, roots or four solutions to that polynomial. Now remember, some of them may come up more than one time, so you could have three distinct with one showing up twice, but a total of four. And this, again, is a fourth degree polynomial, so we're going to have to do some tricks in order to solve this. So the first thing I want to do, or the second thing, is use the rational root theorem in order to try to find some of those rational real roots. So I'm going to look for p, all the factors of the constant. So that's going to be p, which all the factors of 147. I know 1 is a factor. I know 3 is a factor. And that would make 49 a factor. And 147 a factor. And remember, I can look at positive or negatives of each one of these. All right, so I'm going to go to my calculator here and put this equation in. So this is going to be x to the fourth. And that was plus 2x cubed. Plus 46x squared. 46x squared plus 98x plus 98x minus 147. Okay, now that I have that in there, I'm gonna, well, let's go ahead and do this first. I'm gonna find my q. Remember, q is all the factors of the first coefficient. So in this case, it would be the coefficient in front of the x to the fourth term, which is just 1. So it'd be plus or minus 1. So basically, when we look at p over q, all the factors of p over all the factors of q, it's just going to be all of these numbers all over 1. And again, we're looking at both positive and negative. So going up here, we're going to go to second window, make sure that our independent is on ask, and then second graph, go to our table. Oh, look, I'm already having one there. And I'm going to start putting in these numbers, again, both positive and negative. So 1, negative 1, 3, negative 3, and 49, negative 49, and 147, and negative 147. All right, so I did find two roots, because remember, a root is when I plug in the value and I get a 0 in return. So both 1 and negative 3 are roots. So at this point, I'm going to do synthetic division twice in order to get this down to a second degree polynomial. All right, so let's start off, get some more room here. Okay, we're going to start off by just putting down the coefficients of each of these terms. Remember, if we're missing a term, for example, if it were to go from x to the fourth to x squared, we need to put a 0 in for the x to the third term, but in this case, we're not missing any. So I'm going to make a little kind of L-shaped thing like this, and then start putting in these coefficients here, which is 1, 2, 46, 98, and negative 147, negative 147. 47. And I don't think I left myself enough space there, so let me redo that part here. And then I'll first, I could use either 1 or -3, but I'll use 1 first. So I put a 1 on the outside. I bring down the 1. 1 times 1 is 1. Added with 2 is 3. 1 times 3 is 3. Added with 46 is 49. 1 times 49 is 49. Add these together and I get 147. And 1 times 47 is 147. 147. And then I add these, and I should always get 0 at the end. If I don't get 0, then I either picked something that was not a root or my math went awry somewhere. Okay, so now I am going to go ahead and do this again. So this gets it down to a third-degree polynomial, just with the coefficients of the third-degree polynomial. And if I do it now with the -3, that'll get me down to a second-degree polynomial. So very similarly, I bring down the 1. 1 times -3 is -3. I add those together and I get 0. 0 times -3 is 0. Add those together, I get 49. 49 times -3 is -147. And I add those together and I get 0. So again, I get 0 at the end. And now this is a second-degree polynomial. So let's go ahead and start getting these factors. So we know 1 and -3 are roots. So x minus 1 is going to be a factor. And x plus 3 is also going to be a factor. And then we're going to, so that's because we had the 1 and the -3 there. Now we're going to go ahead and write this quadratic. So that's 1x squared, which is just x squared. 0 times x, which is a 0. We don't have to put anything there. And then plus 49. Plus 49. All right. Up. Plus 49. Okay. So the last thing I need to do in order to fully factor this is to set this one equal to 0 and solve. So I'll do that right here. So x squared plus 49 is equal to 0. Subtract 49 from both sides. I'm going to get x squared is equal to -49. And then take the square root of both sides. And I'm going to get x is equal to plus or minus square root of 49 is 7. And because we have a negative, we're going to put an I. So I times this, I times 7 there. Or 7i. Usually we'd write that as 7i. So we have positive 7i and negative 7i. And because that's bothering me a little bit, let me go ahead and just put the I right here. So these are our last roots, which means that we can write these as factors as well, as x minus 7i and x plus 7i. So fully factored, this is going to look like this. X minus 1, x plus 3, oof. So the positive 7i goes with this factor, x minus 7i. And the negative 7i goes with the factor of x plus 7i. And this would be our fully factored solution. All right, if you have any questions, let me know, and have a great rest of your day.